Hey guys, Professor Brown here, and this presentation will cover Chapter 7 from the OpenStax Atoms First Chemistry textbook. In Chapter 7, we are going to start taking a look at chemical equations, their notation. We're going to learn how to balance them, why we have to balance them, and then we'll follow up with looking at some common types of chemical reactions and their common equation characteristics, as well as finishing by writing some of our own chemical equations to describe some reactions. Here on this slide, we have a typical chemical equation that is written for the oxidation of glucose, which is a fancy way of saying we burn some sugar, and this is the representation of the reaction that happened. We have our glucose molecule represented here with C6H12O6. You probably are pretty familiar with these little numbers here that we call subscripts. Those tell me how many atoms of each of that element are in one molecule of glucose. The subscript 6 tells me there are 6 carbon atoms. The subscript 12 tells me there are 12 hydrogen atoms. And the subscript 6 tells me there are 6 oxygen atoms, all in one molecule of glucose. Then we see we have plus 6 O2. So now we have a new number here that you may not be familiar with. This is a big number in front of our chemical formula. Those are present in chemical reactions, and they're what we call coefficients. They tell us how many of that molecule are participating in a chemical reaction. We'll see often that more than one molecule has to participate in order for the reaction to be complete. We'll discuss why in a minute, but for now, just commit to memory that coefficients tell us how many of a molecule participate in a reaction. Then we have an arrow here. We have these two chemical formulas, these two chemicals essentially, being added together. They're reacting together as indicated by this plus sign. We call these the reactants. They are what is reacting. Then we have a little arrow that shows us the yields, meaning these things are going to react together and they are going to yield our products. On our product side, we see the same coefficients as well as some chemical formulas. So in the oxidation of glucose, we see the resulting products are 6 molecules of carbon dioxide as well as 6 molecules as water. And again, we call everything on this side, everything that is produced, we call the products. We're going to take a look at another chemical reaction here now to understand why we might need coefficients. So here we have the combustion of methane. Methane is a simple hydrocarbon. It's the simplest of hydrocarbons, and it has the formula CH4. And we have the molecule of methane depicted here with the carbon atom with 4 bonded hydrogen atoms. Methane reacts with oxygen, as we see in the atmosphere. We see it actually happening here in the animation down below. That is methane reacting with oxygen. Somebody provided it a spark to kick the reaction off, and then there's enough energy in this reaction to keep going as long as there's enough reactants. We see that the products, indicated by our yields arrow, are carbon dioxide and water. Now we actually have a hard time seeing those products because they're pretty well invisible, but we can see the other products, the massless products, the heat and the light that are also products of this reaction. However, when we write chemical equations, we're only concerned with the material, the matter part of the chemical reaction. So the products, the material parts of the products are CO2, we have drawn here, and H2O. So chemical reactions are nothing more than rearrangements of molecules. That is what is known as the law of conservation of matter. We will see if we try to rearrange these molecules as we have depicted, in order for our chemical equation to hold true, there's kind of a problem. One of our hydrogens had to change into an oxygen, and 2 of our hydrogens disappeared. that really seriously violates the law of conservation of mass, which may be the most important law of matter in all of chemistry. It says that matter is neither created nor destroyed in a chemical reaction, only rearranged. So that disappearance of the hydrogen and that changing of one of the hydrogens to the oxygen is a complete violation of the law of conservation of mass, and so it can't happen. We must have the same number of atoms on the reactant side that we have on the product side. Here we have the actual reaction of the combustion of methane. We can see that this better depicts what goes on when the reaction happens. We're going to look at what this chemical equation would look like of the picture described and then show why it works. So we have CH4 here, as we've already described, but now we have two molecules of our oxygen, 2O2, as we would say. We're only showing one molecule of CO2, so we won't need a coefficient there. However, we're also now showing two of the water molecules being formed, so 2H2O as part of our product. Why does that appear more correct than the previous version that we just looked at? Well, if we consider the rearrangement of our one CH4 methane molecule and two oxygen molecules, we can see that the products are produced without having to have anything disappear or anything new appear. Just a simple rearrangement of those molecules and the atoms bonded in those molecules allowed for our products. This would obey the law of conservation of mass, and we would say that this is a balanced reaction. And so the balanced chemical equation for the combustion of methane, like we just established, is one molecule of methane, which is represented here, plus two molecules of oxygen, represented here, gives us one molecule of carbon dioxide and two molecules of water. Notice I have put some little symbols here, G, 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 and L. Those will indicate the state of matter that the substance is in the chemical reaction. G stands for gas and L stands for liquid. We'll also see solid, and sometimes you'll even see AQ, which means aqueous, meaning that that substance is dissolved in water for the chemical reaction. Here's a list of the different symbols you may see used in the chemical reaction or chemical equations. And then they give you some of the, the meaning behind that symbol. Most of the things described here we've already talked about, but you may notice that sometimes you will see a forward and reverse arrow. That indicates the reaction is reversible and sometimes does move in the opposite direction. Sometimes we'll see a delta or a triangle over the reaction arrow. That indicates heat was applied in order to have the reaction go forward. Sometimes you will see NR on one side of the arrow to indicate no reaction. So now we're going to practice balancing some of our own chemical equations. The steps to balancing equations is fairly straightforward. We're going to count the total number of atoms of each element on each side, the product side and the reactant side. If they are equal on each side, then the equation is balanced and we don't have to do anything else. More often than not, especially in the practice problems, they will not be balanced. And so we are going to change the coefficients. Now, that is the kind of overall end-all be-all of balancing chemical equations. You can only change the coefficients. Keep that in mind. Say that with me. You can only change the coefficients. You cannot change the subscripts of the chemical formulas. When you change the subscripts, you've changed what chemical is involved, and you can't change what chemical is involved because that's not the reaction you're describing. You can only change the coefficients. When you change the coefficients, you stop and you see what was adjusted, how many atoms were adjusted by your change. You count again, and if everything is not balanced, you keep repeating until they are. There's one little point of note that I like to make that may make your life easier. If you've become adept at identifying the polyatomic ions, then you may see that you can actually count them as one single entity for easier balancing. You don't need to split them up into their constituent parts. We'll see a few examples of those throughout the next couple of slides. Here on this slide, we have our first chemical equation for balancing. 1 molecule of nitrogen plus 1 molecule of hydrogen yields 1 molecule of ammonia. When I balance chemical equations, you'll often see me draw this line down the yield arrow in order to separate the two sides of which I need to balance my atoms. Then I'm going to go through and count how many atoms of each element I see. On this side, I see 2 nitrogen atoms, and I also see 2 hydrogen atoms. On this side, if I count my number of hydrogens, I only see 1, and if I count my number of hydrogens, I see 3. So I can see that this is not balanced. I do not have 2 nitrogens here, and 1 nitrogen here, 2 hydrogens here, and 3 hydrogens in the products. That cannot be. A hydrogen cannot appear from nowhere, and our nitrogen is not allowed to disappear. So we must adjust our coefficients to make this better reflect reality. If I put a 2 in front of my ammonia in order to make sure that I have 2 nitrogens in my products, I will adjust my 2 nitrogens as I expect. But what I've written here indicates that I make 2 molecules of ammonia, NH3, whose Lewis structures would look thusly. So this is one NH3 here, and this is another NH3 here. You'll notice that leaves me with 2 nitrogen atoms in my products, which is what I want. However, it also leaves me with 6 total hydrogen atoms in my products. It's not too much of a problem because I can adjust just the hydrogens in the reactant side. So in order to finish the balancing of this equation, I will put a 3 in front of my hydrogens over here, indicating that 3 H2 molecules were used. And in 3 H2 molecules, I should find 6 total hydrogens. So the balanced chemical equation for the reaction of nitrogen with hydrogen to form ammonia is 1 molecule of N2 plus 3 molecules of hydrogen yields 2 molecules of ammonia. Here's my next example, the decomposition of potassium chlorate into potassium chloride and oxygen gas. If I draw, I'm going to draw my arrow from my yield sign down, and I'm going to count the elements that I see. The first element I see is potassium with the capital K. I see 1 atom of potassium there. The second atom I see is a chlorine. And I see 1 chlorine in my formula. And the third atom I see is an oxygen. I see 3 oxygens there. And if I go on the other side and I count the same atoms, I see 1 potassium here, 1 chlorine here. However, on this side, instead of 3 oxygens, I have 2 oxygens. So I see there's an imbalance there. Now, for chemical equations, you cannot write anything except for whole numbers as coefficients. Coefficients are always whole numbers. They can't be 0.5s or fractions or anything like that. So therefore, what number can we put in front of this 2? There is no number we can put in front of the oxygen here to make this 2 become a 3. So I'm probably going to end up with both more than 2 or 3 on oxygens in either side. Now that leads me to think, well, with 2 and 3, probably a common multiple of both is 6. So let's try to get that oxygen to 6 and then try the other side. So if I put a 3 here, then I'll have 6 oxygens on this side. I can balance this out now by putting a 2 in front of the KClO3. That changes my oxygens to 6 of them like I want. 2 molecules of KClO3 will have 6 oxygen atoms. However, we'll also have 2 chlorine atoms and 2 potassium atoms. So now I'm still not quite balanced. I've got a little bit of work left to do. Luckily, KCl can be and manipulated on the product side by itself. If I put a 2 in front of the KCl there, that indicates 2 molecules of potassium chloride, which would include 2 potassium atoms and 2 chlorine atoms. So the balanced chemical equation is 2 molecules of potassium chlorate decomposed into 2 molecules of KCl and 3 molecules of oxygen. This is my next example. Sodium chloride plus fluorine gas yields sodium fluoride plus chlorine gas. And I start, as I always do, by drawing me a line at my yield arrow. I will count the elements that I see. The first one I arrive at is the sodium. I see 1 sodium atom, followed by chlorine, where I see 2 chlorine atoms. The next element I arrive at is fluorine, and I see 2 fluorine atoms. In the product side, I will recount the same elements. In sodium, I only see 1 sodium here. I like to keep the same order so that I can make easy comparison on either side of my line. So I'm going to count chlorine next. I see 2 chlorines on the reactant side, or excuse me, on the product side. I see 2 chlorines on the product side. And then I will finish by counting my fluorines, and I only see 1 fluorine there. All right, so I can see that there's an imbalance between chlorines and fluorines. On the reactant side, I have 1 chlorine, and on the product side, I have 2. On the reactant side, I have 2 fluorines, and on the product side, I have 1. I'll begin just arbitrarily. I'm going to try to solve the problem with my fluorine. If I put a 2 here in front of the sodium fluoride, that will give me 2 fluorines, as I would need. It also alters how many sodium atoms I have, however. I'll have 2 sodium atoms after that change of that coefficient. I can try to fix the sodium or the chlorine next, but I'll look on my reactant side and notice that sodium and chlorine are together, which is a good thing. If I put a 2 here, that will show 2 sodium atoms now, and will also give me 2 chlorine atoms. Now I see there's 2 of everything in the reactant side and the product side, in which case everything is balanced. So the balanced chemical equation is 2 sodium chlorides plus 1 fluorine gas yields 2 sodium fluorides plus 1 chlorine gas. Here's our next example, and we see that we are trying to balance the combustion of hydrogen into water, where hydrogen, we're going to draw our line here, and we have hydrogen gas. That is 2 hydrogen atoms. And we have it reacting with oxygen gas, that is also 2 oxygen atoms. And on our reactant side, our product side, we are making a water molecule, and that water molecule has 2 hydrogen atoms. That water molecule also has 1 oxygen atom. So we see the problem here. We lost an oxygen atom, it disappeared, and the law of conservation of mass says that oxygen must be accounted for. It cannot disappear. And the only way we can really fix that here is we can start by adding a 2 in front of our water. That gives us 2 water molecules will have 2 oxygen atoms, but it will also have 4 hydrogen atoms. I can see that I can adjust just hydrogen by itself on the reactant side, so I think I've worked into a situation where I can finish this up. I put a 2 there. I'll have 4 hydrogen atoms on the reactant side. So the balanced chemical equation for the combustion of hydrogen into water is 2H2 plus 1O2 yields 2 H2O molecules. On this slide, we have our first example that includes some of those polyatomic ions that I was talking about. So if you'll notice, we have one of those instances where we have a substance or a chemical formula that has some parentheses in it. That is because of the sulfate ion here is one of our polyatomic ions. It is always SO4. And since it is always SO4, you can count it as just SO4 as one thing and not have to count out the individual sulfurs in the oxygen. It really will make life easier sometimes. Otherwise, we just proceed normally. So we'll count the entities or the elements that we arrive at. Al, I see one aluminum atom on this side, and that's the first one I run into. The next one I run into is the bromine. I see 3 of the bromine atoms. The next atom I see there is potassium, and I see 2 potassiums. I know I covered it up a little bit, but there's 2 potassiums there. And then finally, the sulfate group that we talked about, because we can identify that as a polyatomic ion, we're just going to count it as one entity, one almost like an element. However, we need to recognize that if it's there by itself with no parentheses around it, that means there is one sulfate group there. I like to keep the same order, so I'm going to count the aluminums on this side now. Aluminums I see 2 of over here. Bromine was next. I only see 1 bromine on this side. Potassium was next. I only see 1 potassium on this side. And then finally our sulfate groups were last. And I see 3. There's 3 on the outside of that parentheses. So there's 3 sulfate groups on the product side, or yes, on the product side. And all right, so we can adjust these things, probably starting with the sulfate group. If I put a 3 over here, that would adjust. That would mean I have 3 sulfate groups there, because 3 potassium sulfates would have 3 sulfate groups. But it would also mean I have 6 potassiums. 6 potassiums. And I could adjust that. I could adjust the potassiums on this side by putting a 6 here. Would give me 6 potassiums. And then I still have to adjust the aluminum and the bromine. If I put a 2 here, that would change this to 2 and this to 6. I do have 6 bromines over there because of the 6 in front of the KBr. And so that looks like, and we have a balanced chemical equation. We have 2 aluminum atoms on both sides, 6 bromines, 6 potassiums, and 3 total sulfate groups on both sides of the chemical equation. So that is balanced. 2 aluminum bromides react with 3 potassium sulfates to give us 6 potassium bromide and 1 aluminum sulfate.
Here in this example, we are given a sentence form of a chemical reaction, and we are responsible for transcribing these compound names into their chemical formulas and arranging the reaction as the words here put it. We see sodium phosphate and calcium chloride react to form calcium phosphate and sodium chloride. And so if I'm going to write that out in chemical equation format, then I'll need the formulas for sodium phosphate and calcium chloride first. These are ionic compounds. I can kind of readily see that by noticing the metal comes first, followed by some other non-metal ion. When we see the metals in general chemistry, we're often thinking of ionic compounds. And so I would use the charges to determine the formulas for each of the compounds there, and I would come up with the fact that sodium phosphate is Na3PO4, and it says it reacts with calcium chloride, which would be CaCl2, to form, and put my yield arrow here, calcium phosphate, which would have the formula CaPO4. We'll need 2 of those, and sodium chloride is our final product there. So we utilize the nomenclature information we learned from previous work to write out the chemical equation that they have described here, and now we're ready to balance it. So if I put my line at my yield arrow, I will count elements as I arrive at them. I see 3 sodium atoms, 1 phosphate ion, 1 calcium atom, and 2 chlorine atoms. And if I take the count on the other side, I see only 1 sodium over here. Phosphate groups, I see 2 of. Calcium atoms, there are 3 of. And chlorines, I only see 1. So I have my initial count here. I'm ready to adjust my coefficients and see if I can get these columns even. I know I'm going to have maybe 3 sodiums over here. So I will try that. And that means I would have 3 sodiums and 3 chlorines, which may seem like it would work, but then if I look over here, I see I have 2 chlorines on this side. So I have a 2 chlorine and a 3 chlorine situation. So I'm thinking maybe I'm going to try to get those numbers to 6 instead of 3. And to do that, I would actually put a 3 over here in front of the calcium chloride. That would change calcium to 3 here, and that would change chlorine to 6. And so now I can make those other, now I can make the chlorines even by changing this to 6 instead. Use my eraser here. Get rid of that 3. And I'm going to put a 6 there. Now that means my sodium is 6 and my chlorine is 6. Calcium is 3. And sodium is not balanced. And if I try a 2 here, that leaves me with the 6 sodium atoms I want. It also means I have 2 phosphate ions. And so if I compare the columns now, I see 6 sodium atoms on either side, 2 phosphate ions on either side, 3 calcium atoms on either side, and 6 chlorine atoms on either side. If I check my coefficients here, 2, 3, 1, and 6, because there's a 1 there, there is no other common denominator that we could reduce these by. So everything is balanced and the coefficients are in the lowest form, so we could call this the balanced form of the reaction between sodium phosphate and calcium chloride to produce calcium phosphate and sodium chloride. We have another example of a word equation here that we're expected to write out into a symbolic chemical equation. This one reads a little differently. It says potassium metal and chlorine gas combine to form potassium chloride. So there's a couple of things that we need to remember as we read this sentence here, and to kind of understand what forms of these materials they want us to write down. So when you read a sentence that refers to a chemical equation and it says something like potassium metal here, the word metal there is the operative part of this sentence, where it says potassium metal here. What they're trying to convey is that the potassium is in its elemental form. So it is essentially by itself. There are no other atoms or elements bonded to our potassium. So when we write a metal in our chemical equation, it is just the symbol of that element, because metals can react as single metallic ions. Now, in contrast to that, it says there's chlorine gas present to react with our potassium metal. And so when they say chlorine gas, they also mean that chlorine is in its elemental form. But chlorine is one of the what we refer to as diatomic elements, meaning in its elemental form it exists as a 2-atom molecule of itself. And so there's actually 7 different elements that we write this way. When they are present in their elemental form, we write them as Cl2, because that's what is in chlorine gas. That's what exists as chlorine gas is Cl2 molecules. So potassium metal and chlorine gas combine, we can put our yield arrow now, to form potassium chloride. Now when we see potassium chloride, that is now an ionic compound. So we have to follow the ionic nomenclature rules to get to the formula for that compound. The formula for this would be KCl after we balanced our charges. So potassium metal K plus chlorine gas Cl2 reactive form potassium chloride KCl. We can see that this is not balanced if we put our line down the middle, count our elements, 1 potassium atom, 2 chlorine atoms. On the other side, 1 potassium atom, 1 chlorine atom. So we will certainly have to start by putting a 2 there. That will give us 2 potassium atoms and 2 chlorine atoms. I already have 2 chlorine atoms on this side, so if I just put a 2 in front of the K here, that will finish my balancing, and the correct balancing for this reaction is 2 potassium plus Cl2 reacts to form 2 KCl units. We have another example here on this slide. We have hydrogen gas and nitrogen monoxide react to form water and nitrogen gas. So in this example, we are tasked with writing out the formula for hydrogen gas, a covalent compound that react to form a gas and another covalent compound that hopefully we know the formula for. So when we write this one, hydrogen is one of our diatomics, meaning when it's present in its elemental form as a gas, it's present as a 2-atom molecule of itself. And so, of course, we will write that as H2. We react that with nitrogen monoxide. So that is a covalent compound. There is no prefix on the first one, so there is just one there. There is only one O, so NO is the formula for nitrogen monoxide. Reactive form is where we put our yield arrow, water, and nitrogen gas. Nitrogen is a diatomic, so in its elemental gaseous form, it is a 2-atom molecule, N2. H2 plus NO react to form H2O and N2. We'll put our line here. I'd see 2 hydrogen atoms there, 1 nitrogen atom there, 1 oxygen atom there. I see 2 hydrogen atoms here, 2 nitrogen atoms, and only 1 oxygen atom. So everything is balanced here except for the nitrogens. If I balance the nitrogen here, that will give me 2 nitrogens, but will also give me 2 oxygens. That means I will need a 2 here in order to give me 2 oxygens, but it also gives me 4 hydrogens. I can balance that by putting a 2 here to give me 4 hydrogens, and that gives me the balanced form of this equation, 2 hydrogen molecules plus 2 nitrogen monoxide molecules react to form 2 water molecules and 1 nitrogen molecule. So now we're going to go over some of the common chemical reactions, learn what some of their patterns are, and even how to predict the products of some chemical reactions between compounds without giving the products expressly. Before we do so, though, one of the types of reactions that we deal with concerns whether or not the product is soluble, meaning does our product dissolve in water, and this specifically is geared toward the solubility of certain ionic compounds. And so there are these tables that we usually call solubility charts or solubility tables that help us determine whether or not a compound, a certain ionic compound is soluble. And this is the example that we have from our text here. On top, we have soluble ionic compounds and insoluble ionic compounds. And I'll kind of give you a bit of a rundown of how to read these. So we see everything up top. It says soluble ionic compounds contain these ions, the NH4 ion, and the group 1 cations. The lithium, sodium, potassium, rubidium, and cesium. So pretty much, and you can see there are no exceptions there, pretty much all of those, any compound containing those ions is water soluble, meaning they will stay dissolved in the reaction. We also see that anything containing chlorides, bromides, and iodides, for the most part, is soluble, but there are some exceptions there. So it says that any of these combinations with silver or mercury or lead are insoluble or are the exception. So that means they will not dissolve in water. So for instance, silver chloride does not dissolve in water. It is an insoluble compound. The same would go for silver bromide and silver iodide. Also mercury 2 chloride, mercury 2 bromide, as well as lead 2 chloride, lead 2 bromide. So then we can see any fluoride is soluble except for those mixed with the group 2 metals. So that's things like calcium and magnesium, lead 2+ and iron 3+. So all of those would be soluble except for those few exceptions. Then we can see acetate, bicarbonate, nitrates, and chlorates. All of those are soluble. Anytime you see that in a compound, that compound is soluble. And then we have some sulfate. A lot of sulfates are soluble except for when it's a silver sulfate, barium sulfate, calcium sulfate, lead sulfate, or strontium sulfate. And then on the bottom, we see the insoluble ionic compounds. These ions are very often insoluble. The carbonates, the chromates, the phosphates, and the sulfides are often lead to insoluble compounds. And you can see there are a few exceptions there, as well as the hydroxides. A lot of times they are insoluble. We'll look at some examples in the next few slides of how you might want to read these to get yourself familiar with using a solubility table. So our first example here is sodium nitrate. Is sodium nitrate soluble in water is the question we want to answer, and we have our resource here, our solubility table, to help us do that. So sodium nitrate is the NaNO3 would be the formula for sodium nitrate. And if we look over here and see, we can check a couple of ways. We see, if I look for soluble ionic compounds, I'll see soluble ionic compounds contain these ions, with sodium being one of those ions, and there are no exceptions for sodium, it looks like. So I could say, just from the fact that there's a sodium ion there, this is an ionic or a soluble ionic compound, so sodium nitrate will dissolve in water. I also see that pretty much if I look further down there, the nitrate ion is also listed on soluble ionic compounds with no exceptions. So I feel pretty confident saying that this compound is water soluble. Here's our next example, calcium hydroxide, and we will write out the formula for calcium hydroxide first. So we can see what ions are involved. Calcium is Ca, and it's a 2+. So when we write the hydroxide ion here, OH, we'll need a 2 for our hydroxide ion. The formula for calcium hydroxide is CaOH2. We can see that if we look down our list here for one of our ions, the first one that I find, well, I don't see calcium. I don't see anything about group 2 so far. Here's a group 2 beside the fluorine, but that doesn't really apply to us. The last one on the list there is our friend hydroxide, and we see that hydroxides are only soluble when they're compound with group 1 metal cations. Calcium is a group 2 metal cation, so that means it is insoluble. Calcium hydroxide does not dissolve in water in any appreciable amounts. So here's our next example, silver nitrate. Silver nitrate has the formula AgNO3. Silver is a +1 ion, nitrate is a -1 ion, so you need one of each. AgNO3 is the formula for silver nitrate. If I go and check the solubility rules here that I have in front of me, if I look for the first one I arrive at that I see here, I don't see any silver anywhere, but I do see the nitrate sitting here. And nitrate is part of the soluble ionic list with no exceptions. So all nitrates are soluble, meaning that silver nitrate is a soluble ionic compound. It does dissolve well in water. Here's our next example, magnesium sulfate, which would have the formula MgSO4. Magnesium is a 2+ ion, sulfate is a 2+ ion, so when they are compounded together, you need one of each to balance the charges. MgSO4, the first formula that I run into, the first ion that I run into as part of my compound is the sulfate ion here. And it says that sulfates are soluble as long as they are not compounded with silver, barium, calcium, mercury 2, lead 2, or strontium 2. Magnesium is none of those things, so magnesium sulfate should be a soluble ionic compound, and it does. Magnesium sulfate dissolves well in water. And now, before we start our study of the different types of chemical reactions that are common, we will kind of remind ourselves of what these different little symbols mean in a chemical equation, because they become important when we talk about precipitation reactions here shortly. When we see the little S beside our chemical formula, that means that compound is in the solid form, or that element is in the solid form. When we see the L, that means it's in liquid state. When we see G, that means it's in the gaseous state, like we see with the H2 here in this example. And then finally, when we see aqueous or AQ, like we see here, that means that compound or that element is dissolved in water. So this is the first type of reaction we are going to familiarize ourselves with. This is called a precipitation reaction. Precipitation reactions happen when we dissolve two ionic substances in some water and mix them together and form a new solid product. There's a couple of different names that you may hear attached to these type of reactions. They are double replacement, double displacement, or metathesis reactions. They all kind of mean the same thing. There are just different names for this type of reaction. And it's important to note that this reaction only happens if both reactants are soluble. So the two reactants have to be able, you have to be able to dissolve them into water. And then one of the products formed by the rearrangement of the ions must be insoluble for this type of reaction to take place. You see a general scheme of what happens in a precipitation reaction below. We see two ionic compounds represented by A, B, and C, D. And AB represents an ionic compound with cation A and anion B. So you could think of something like sodium chloride. Sodium would be A and chlorine would be B. And then compound CD is another ionic compound, something totally different, maybe magnesium sulfate. Mg would be C, the positive metal. Mg would be C, and the negative sulfate ion would be D. So in the precipitation reaction, the cations switch places. When you dissolve these things down into water, all of the cations and anions separate from each other. And when you pour them together, they mix up and recombine. So some of the solid or some of the metal ions A end up bonding with anions D, and vice versa. Some of the cations C end up bonding with the anions B. And so you get this rearrangement or displacement, replacement of the ions from the reactants that we see there. So we'll take a look over the next few slides at some actual examples and even some videos of what a precipitation reaction will look like. So here on this slide we have, you can actually see a precipitation reaction take place. In solution 1, we have lead 2 nitrate dissolved, and in solution 2, we have some potassium iodide dissolved. So let's try to figure out what the product there produced is from our reaction. So lead 2 nitrate has the formula PbNO3 2. So if I were to write the formula out using the rules that I've established for writing ionic formulas, which says I must balance the charges. Lead 2 is a positive 2 ion, nitrate is a negative 1 ion, and so to balance them out, I would need 2 of the nitrates and 1 of the lead, resulting in the formula PbNO3 2. It is in aqueous solution. I can see that from the fact that it's dissolved in the water there in the clip. I react it with potassium iodide. Potassium is a +1 ion, iodide is a -1 ion, so I only need one of each to form potassium iodide, Ki. Now, it is also in the aqueous state. So, if I treat this as one of my double displacement reactions or metathesis reactions or precipitation reaction, it's certainly a precipitation reaction. We can see the precipitation happen here in the clip. So what happens in a precipitation reaction is the ions switch places. So the lead is going to switch place with the potassium, which is going to switch place with the lead. It's going to each one is going to replace those ions. So let's see what happens when we replace those ions. If I replace, keep in mind, this is lead 2. If I replace lead 2 with the potassium and bond it with the iodide instead, the new formula formed would be PbI2. I have to keep in mind that the lead has a +2 charge, so when I combine him with iodine in the products, I must make sure that their charge is balanced and that I have the right formula for lead 2 iodide. And the right formula for lead 2 iodide is PbI2. When potassium bonds with nitrate, potassium is a +1 ion, always. Nitrate is a -1 ion. Always. We learned that from our polyatomic ion chart. So KNO3 is the correct formula for potassium nitrate. Now, at this point, if I didn't have the clip here showing me that this is a precipitation reaction, I would want to see, does this reaction actually happen? And if we remember from the first slide, to meet the conditions of does this reaction actually happen, I have to determine, first of all, are my first two components water soluble? And they are water soluble because I do see that they're dissolved in water in the clip. In the reactants, I will also go and check and see if they are water soluble. Now, what I will notice if I go and check a solubility table is that potassium nitrate is water soluble. So since there's a bunch of water there, it stays dissolved. And then I would see, if I went and checked the iodide, I would see that lead iodide is insoluble. So when I mix these two solutions together, lead iodide is made. And because it is insoluble, That is actually the really neat looking yellow stuff that you see, this solid lead iodide formed from that reaction. Now, just a point of note here, if we don't have the clip, if we're not sure if this is a precipitation reaction, we would go through and check the solubility of every species there that we made. If we see that they're all able to be dissolved, they're all aqueous, we would actually say that no reaction happens, because when we poured them together, everything would just stay dissolved and no new compounds would be made. So both reactants have to be water soluble, and at least one of the products must be insoluble for this reaction, for this type of reaction to take place. On this slide, we have our next example of a precipitation reaction. This one certainly takes place. We can see it taking place here, but we're still going to try to make sense of the compounds that are used and the compounds that are formed, see what that solid product there is appearing in our solution. So it says solution 1 is sodium phosphate. Sodium phosphate would have the formula Na3PO4. Sodium is a 1+ ion. Phosphate is a 3- ion, giving us the formula that you see there. It says that copper 2 chloride is the second solution. So chloride is a -1. If we're using copper 2, that means we were going to end up with CuCl2 as our other reactant. Now, in a precipitation double replacement reaction, we know that the ions switch places. So we're going to have the sodium with the chloride and the phosphate with the copper. Sodium chloride is a pretty easy one. Maybe we know that one by now. NaCl results from the combination of sodium and chloride ions. If we have copper 2 being combined with phosphate, copper 2 is a 2+, obviously, and phosphate is a 3-. So that will result in the formula Cu3PO4, and we'll need 2 of those to get our charges balanced. We know that the first 2 compounds are soluble because they're sitting there dissolved in solution. So we could check, but I'll just go ahead and write AQ out the side of those. And then we can make way with determining which one of those 2 products there is the solid form. Sodium chloride, you may already know, is soluble, but we'll go ahead and check. If we go down our list here, we run into chloride. Actually, we run into sodium here. We see that sodium is part of the soluble list with no exceptions. So it's pretty safe to say that sodium chloride is soluble. All chlorides are soluble, in fact, unless they are combined with silver, mercury 2, or lead 2. And that is not the case here. It's just combined with sodium. Good old sodium chloride is definitely soluble. So that's the aqueous solution. That probably means our copper 2 phosphate is the culprit for the precipitate there, but let's make sure. If I look down my my solubility table here, I see that, let's see, the first one that I run into is phosphates. I don't see copper on there anywhere, but I do see phosphates. And it says phosphates are actually insoluble unless they are bonded with group 1 cations, so sodium, potassium, lithium, etc., or ammonium. That is not the case here. Copper is neither a group 1 cation nor is it ammonia or ammonium, NH4. So that means that that is an insoluble product, and therefore that is the solid that we see forming there in the beaker. So this is a good example of what you may be asked to determine with respect to the precipitation reactions. You'll be given 2 different compounds and asked, do they react in the double replacement way, or does a reaction occur between these 2 compounds? And to do that, what you do is you write out the chemical formula, and then you check to make sure it abides by the double replacement guidelines, in that both of your reactants are soluble in water, and at least one of your products is insoluble in water once the ions have been switched. So we see here we're asked potassium sulfate and barium nitrate. Do they form a double replacement reaction? And to determine that, we will first write each of these formulas out. If we remember, potassium is a +1 ion and sulfate is SO4 with a 2- charge, then the resulting formula would be K2SO4. The reaction here is barium nitrate. So barium is symbol Ba, and it's a 2+ ion. And the nitrate is NO3 with a 1-. So the formula for barium nitrate is BaNO3 2. And that will react. If we assume that it reacts in the way that a double replacement reaction takes place, then we will have potassium bonding with the nitrate and barium bonding with the sulfate. Potassium and nitrate are both 1+ and 1- ions, so the resulting formula should be KNO3. Barium and sulfate are a 2+ and a 2- ion, so their formula will be BaSO4. All right, now that we have the correct formulas for the possible double replacement reaction written out, we'll go through and check the solubility of each species and see if it lines up with the correct double replacement or precipitation paradigm. So potassium sulfate, it says that if I look through my solubility table here, first thing I see is potassium. Potassium is part of the soluble compound list without any exceptions. So that will be able to dissolve in water. That's an aqueous solution. If I look down my list to determine whether barium nitrate is soluble or not, I don't see any bariums right off the bat. I do see the nitrate group, and it says that nitrates are soluble ionic compounds without exception. So that can be dissolved into aqueous solution. Now, what happens when I mix those two solutions together? Are any of the formed products insoluble? Well, if I look through potassium and nitrate, I see they're both on the soluble list with no exceptions. So I know that potassium nitrate can and will stay dissolved in that aqueous solution. Our final species there is barium sulfate. Let's check the solubility of that guy. It says the sulfates are soluble as long as they are not bonded with silver. Oh, look at there, barium 2+. If sulfate is bonded with barium 2+, it is insoluble. It's an exception there. So that will form a solid, and that will form a double replacement reaction. So if I were to take aqueous solutions of potassium sulfate and barium nitrate and pour them together, we would see some precipitate of barium sulfate like what we've seen in the previous clips on those earlier two slides. Here's our next example of a precipitation system. So we would be told that lithium chloride and silver acetate, or asked if they would form a precipitate if they were mixed together. And so we start by, again, writing out the chemical formulas for the two compounds that were given. We'll check and see if they can be dissolved in water to even attempt the reaction, and then we'll see if we can figure out what compounds would result if we mix the ions. And so lithium chloride, both lithium and chloride are 1 ions, lithium being a +1 and chlorine being a -1, makes the formula for lithium chloride LiCl plus silver acetate. So silver is Ag, and it's a +1 ion. Acetate is actually this guy right here, C2H3O2, and it has a -1 charge, so the silver acetate formula is AgC2H3O2. They would react to form as long as they are soluble. So if we check our table here, we see that all lithium ions are soluble and all chlorine ions are soluble, with a few exceptions. Lithium is not one of them, so lithium chloride should be soluble. We can dissolve it in water and call it aqueous. Silver acetate is, as we've already pointed out, the acetate ion here. It says that all acetate ions are soluble ionic compounds with no exceptions. So this is soluble in water. We could put it into aqueous solution. If we switched all of those ions around, we find that we have a pretty easy job here because everything is a 1 ion, whether it's positive or negative. Lithium's positive 1, chlorine's -1, silver's positive 1, acetate's -1. So there's not a lot of difficulty in writing the formulas. We can just switch the ions around there. Lithium acetate is Li, C2H3O2, and silver chloride is AgCl. And so again, we check our ionic compound solubility. We see that the acetate ion is, all compounds with the acetate ion are soluble with no exception. So we can feel pretty confident in saying that lithium acetate there would be soluble. And furthermore, let's check our silver chloride. We see chlorides in general are part of the soluble ionic compound group. So most things with chloride ions are soluble. However, the exceptions are, we'll look at there, Ag plus is our exception here. So if chlorine is bonded with silver 1 plus, then that will form an insoluble compound. So silver chloride there would be our solid, and this would be a viable double replacement reaction. We could go through and check, but because everything was positive 1 or -1, that whole reaction should be completely balanced without having to balance it already. In our last example of how to predict double replacement reactions here, I'm going to show you one that actually does not work. So an example that would lead to what we call no reaction. So it says, determine if a double replacement reaction can occur between calcium chloride and sodium nitrate. And I would start this problem like I do any other. I would put my two reactants down in chemical equation format and see if both of them were soluble compounds. And if I write out the formula for calcium chloride, I would find that calcium chloride is CaCl2 plus sodium nitrate is NaNO3. And I can see that for chloride ions or chloride containing compounds, all of them are soluble with a few exceptions there, but none of them are calcium. So that would be an aqueous compound that we could dissolve in some water. Nitrate, all nitrates are soluble with no exception, as well as all sodium containing compounds being soluble with no exception. So sodium nitrate is certainly a soluble compound. And then if I rearrange those ions, I would find that sodium chloride, of course, has the formula NaCl, and calcium nitrate has the formula CaNO3 too. And so like I normally do, I would go and check and see if these are soluble or insoluble compounds. Sodium chloride is a chloride, and chlorides are soluble as long as they are not with silver or with mercury or with lead, and sodium is neither silver nor mercury nor lead, so sodium chloride is soluble. Again, all nitrates are soluble without exception, and so this also would be a soluble compound too. So we would actually say that CaCl2 plus NaNO3, they would still both be aqueous, because if we were really viewing this in a laboratory somewhere, what we would have is a beaker with some dissolved calcium chloride, in a beaker with some dissolved sodium nitrate. And so there would be clear solutions that appeared to just be pretty much normal water. We would pour the two beakers together into a third beaker or pour one into another, and nothing would happen because everything would stay dissolved. Any compounds that could be made that would precipitate out of the solution, as we've seen, would not form. They would stay dissolved into aqueous solution. And so the correct response to this one is NR, which stands for no reaction. Sometimes we see the double replacement reactions symbolized with the net ionic equation instead of the complete ionic equation. And I'll show you what that looks like here. We have a regular double replacement reaction written at the top in our standard molecular chemical equation format, where we have calcium chloride reacting with silver nitrate to form calcium nitrate and silver chloride. Everything is soluble except for the silver chloride product, so it would form a precipitate. In the next line, we see the complete ionic equation. And so the idea here is when you dissolve ionic compounds in water, they're no longer that compound. They're actually split into their individual ions. And so when we write the ionic equation, we show those ions split up. We can see that when we dissolve calcium chloride, we get a calcium ion. So this calcium ion comes from the calcium chloride. And we get two chloride ions. Because there are two chlorine ions, we get two chloride ions when the calcium chloride formula breaks apart. If we have two silver nitrates, this is an already balanced equation. If we have two silver nitrates, then we get two silver ions out of it, and we get two nitrate ions out of it. And so we've shown all of those ions separated because when we dissolve them in water, they actually do separate. After the reaction, we still have some calcium nitrate ions or calcium ions because calcium nitrate is aqueous. So it is soluble, meaning it stays dissolved in that water. So the ions are actually separate. And so the ionic equation shows them separate. We still have the nitrate ions because the calcium nitrate is soluble. So since there's two of them for every one calcium atom, two nitrate ions for every one calcium atom, we actually show two. That's what we have, the two here, two nitrate ions. But then the final one there, we do not show the ions for the insoluble product because they bond together and they fall out of that solution. They are not surrounded by water molecules. They are actually bonded together. And then if we cancel all of the ions on both sides, any free ions on both sides, calcium and nitrate, we're left with an equation that shows the process that takes place to form the precipitate. And that's what we call the net ionic equation. So just the reaction that actually gives us the precipitate. And the reaction that gives us the precipitate is a chloride ion reacting with one of the silver ions to give us silver chloride solid precipitate. Everything else, everything that I've canceled out up here, that just sits there and doesn't do anything and just watches, we call those spectator ions. So on this slide, I'm going to give you an example of how to determine a net ionic equation. We see determine the net ionic equation between potassium sulfate and barium nitrate. The first thing you need to do is write out your typical molecular chemical formula using the nomenclature rules that we've learned a few weeks ago. So potassium sulfate, if you look at a polyatomic ion chart and find a periodic table, you can come up with the formula for potassium sulfate as K2SO4 plus barium nitrate is BaNO3 2. So if they react and we were to form new compounds with by rearranging the ions, we would have potassium nitrate, which has the formula KNO3 plus barium sulfate, which is BaSO4. All right, and so we have our molecular chemical equation for this compound. We're going to now balance this equation, and we would see that balancing can be achieved by two nitrates, placing a 2 here. Yes, by placing a 2 there. And our molecular equation is complete. Now we'll try to write the ionic equation. So when I dissolve, or now I'll go through and check rather what is soluble and insoluble. So if I check my solubility rules, I would find that potassium sulfate is soluble, barium nitrate is soluble, potassium nitrate is soluble, and barium sulfate would be our insoluble solid. Now I'm going to break all of these apart into their ions. So a potassium sulfate formula, when I dissolve it in water, it busts apart into 2 potassium atoms, 2 K pluses, plus 1 sulfur or 1 sulfate ion, SO4 minus. Barium nitrate will dissolve into barium 2 plus ions, and there are 2 nitrate ions, 2 NO3 ions in 1 barium nitrate formula unit. Then we put our Euler arrow that's there. Potassium nitrate, there's 2 potassium nitrate units there. So when those dissolve, I will get 2 K plus units, as well as 2 NO3 units. Now, the barium sulfate does not dissolve. It is a solid, so we leave it together, BaSO4. So now we can determine what our net ionic equation is by canceling the same ions on either side. So I see the 2 K pluses can be canceled. They are spectator ions. The 2 nitrates can be canceled. They are spectator ions. So the net ionic equation here is SO4 minus plus Ba2 plus gives us barium sulfate, solid. So another example here with lithium chloride and silver acetate. If I were to write out the formulas of each, I will find that lithium chloride has the formula LiCl. Silver acetate is AgC2H3O2. If I switch those ions around, I find that the formula should be ALiC3H3C2H3O2 plus AgCl. If I go and use a solubility chart to check my solubility rules, I will find that lithium chloride is soluble, so I can list him as aqueous. Silver acetate is soluble, so I can list him as aqueous. Lithium acetate is soluble, so I can list him as aqueous. Silver chloride is not soluble, so he will be listed as a solid. If I bust everything into the constituent ions that are there in solution, I see that lithium 1 plus ions would be there from lithium chloride. Chlorine, 1 minus ions would be there from chlorine. Silver, 1 plus ions from the silver acetate, as well as acetate ions, 1 minus from the silver acetate. On the product side, I have some lithium ions in solution. Lithium acetate is listed as aqueous because it is solid, meaning they are lithium 1 plus ions throughout the solution. We also have acetate ions because our lithium acetate is in solution. We don't have any silver or chlorine ions, however, because silver chloride is an insoluble precipitate solid. So now we have written our complete ionic equation. Now if we cancel ions on either side of the arrow, we are left with our net ionic equation, which says that Cl1 minus plus Ag1 plus yields AgCl solid. So this would be the net ionic equation for the formation of silver chloride from lithium chloride and silver acetate. Here we'll take a look at another very typical type of reaction, and that is the acid-base reaction. You may, even before you come into some chemistry classes, lots of people have at least an idea of what acids are, maybe bases, and they probably already know or may have an idea that an acid and base will neutralize each other, and that's ultimately what we're going to take a look at in the scheme of acids and bases in this section is what that neutralization reaction looks like. Before we do, though, we will take a few minutes to kind of define the acid and base system and what the different parts are. And then, of course, if you take Chem 2, you will get a further treatment of acid and base chemistry. But we'll take kind of a simple view here at the beginning to be able to find our bearings when it comes to acids and bases. And so acid-base reactions occur when a hydrogen H plus ion is transferred from one species to another. So anytime a single hydrogen ion moves in a chemical reaction, that's considered an acid and base interaction. It's really, really important because there are lots and lots and lots of acid and base interactions that take place in living systems. Acid and base interactions is a very common driving factor in all of the chemical reactions that take place in our body, and understanding that kind of chemistry is really, really important to our current understanding of medicine. Acids are any compound that has the H plus ion and gives it to something else. If we dissolve an acid in water, it will transfer that H plus to one of the water molecules there. So H2O becomes H3O plus, a water with an extra hydrogen attached when you dissolve an acid in it. And then bases are a different kind of compound. They are any compound that dissolves and gives us hydroxide ions. So that OH minus polyatomic ion, the hydroxide that we see quite often in our different chemical formulas, that is the indication that that compound is a base. When a base dissolves, we get OH minus ions in the solution. And so any compound that dissolves and gives us OH minuses is what we call a base. Here we have a diagram of how quite possibly the most common acid, hydrochloric acid, is formed. We see on the left-hand side there the hydrochloric or HCl compound. If it is pure, it is just a gaseous substance with hydrogen bonded to a chlorine atom. It's when you dissolve that substance in water that it becomes the very common hydrochloric acid. So we show that diagram here, the HCl gas dissolving into the liquid H2O to go from HCl gas to HCl aqueous. When that happens, though, there is an acid-base interaction that takes place. The HCl here gives this hydrogen ion here to the water molecule, leaving us with a bare chlorine ion that lost its hydrogen and an extra hydrogen on the water, which also gives the water molecule a positive charge. That's called a hydronium ion, and that's how hydrochloric acid is formed when HCl dissolves in water. So since we've established that acids are compounds that dissolve into water to give us H plus ions, it is pertinent to take a break and talk about the difference between strong acids and weak acids. So unlike ionic compounds that dissociate 100% when they dissolve in water, acids don't necessarily always follow that same pattern. The acids listed here on this table do. They are called the strong acids. They are HBr, hydrobromic acid, HCl, hydrochloric acid, HI, hydroionic acid, HNO3, nitric acid, HClO4, perchloric acid, and H2SO4, sulfuric acid. Those are all of these acids all dissociate completely into their constituent ions. In the case of, for example, HBr, when you dissolve HBr in water, every last HBr molecule separates into H plus and Br minus. These are the only acids that occurs for. There may be a few other strong acids out there, but there's not many, 10 to 15 total, and these are the most common ones. On the other hand, there are millions of weak acids that do not dissociate completely. We'll take a look at that on the next slide, but these are the strong acids. They dissociate completely, and there's very few of them, and the most common ones are listed here. So, like I said, here on this slide we have examples of some weak acids and what their reaction with water looks like. We haven't seen too much of this yet, but this is what we call acetic acid. Notice it is the acetate ion right here. It's the C2H3O2. They just got the C's split apart. So this is the acetate ion that we've seen a few times already on the polyatomic ion chart. But instead of having a typical metal as the cation, we have hydrogen, just a H plus ion here instead to counterbalance the negative charge. And so when you mix this acetic acid with water, it dissociates into the acetate ion. See, the acetate ion has lost its hydrogen because it is an acid, so that hydrogen is lost to the water molecule, forming H3O plus. However, notice there are a double arrow in the reaction in the chemical equation here. And the reason there's a double arrow is because this is a dynamic process. Both the forward and the reverse process are happening at the same time. And in the case of acetic acid, the reverse process is actually happens faster than the forward process. So at any one time, only about 1% of these ions have been changed into CH3CO2 and H3O plus. The rest of them are just sitting fully together as CH3CO2H dissolved in water. They're still dissolved in the water. They are just not dissociated into their separate ions. This is how most acids actually behave in aqueous solution. Those acids that we mentioned that are very common hallmarks of biochemistry. The chemistry inside living organisms is very much based around these equilibrium systems of acids and bases in different aqueous environments. You can see a diagram here on this slide of the separate strong acids and weak acids, we can see when we pour the strong acid into water, every last one of these molecules will separate into its constituent ions. However, we see that's not quite the case for the weak acids. And keep in mind, there are many, 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 many more times more weak acids than there are strong acids. The only strong acids, with a few exceptions, are the ones that we saw on the previous slide. Just as we have strong acids and weak acids, you may guess that we also have strong bases and weak bases. The definition for the difference between strong and weak is the same here. Strong bases dissociate completely when you dissolve them in water, and weak bases do not dissociate 100% when you dissolve them in water. We'll take a look at the strong bases here. The strong bases are all metal hydroxides. So all of your strong bases are ionic compounds formed from some metal, generally something like sodium or potassium or lithium, and the hydroxide polyatomic ion. Since these are ionic compounds, the ones that are soluble, when they dissolve in water, all of the ions break apart into their constituent ions. So that means that they are strong bases. Anytime you see sodium hydroxide, potassium hydroxide, lithium hydroxide, magnesium or calcium hydroxide, those are the most common ones. They are a strong base and they dissociate completely into the metal positive ion and the hydroxide negative ion. Here we have another example of an acid-base system. This is perhaps the trickiest ones to understand. These are the weak bases, and much like the weak acids, they do not dissociate completely. In fact, you can see in this example here, the species that forms the OH minus ion is actually not present in the reactants, and that's what makes the weak bases tricky. A lot of times in the weak base examples, water is the acid. We can see that the hydroxide ion is actually formed when the water donates one of its protons to the ammonia molecule. In this case, this reaction represents how ammonia solutions are formed. NH3 is generally, or in compound formed, a gaseous substance, has to be carried in big tankers like this. To form the ammonia that we see on the store shelves for cleaning, they dissolve it in regular water, and there's actual chemical interaction between the ammonia and the water molecules. So, and like I said, the water donates one of its hydrogens to the NH3, giving us the NH4 plus and the OH minus. And as we said, with the weak acids and bases, this doesn't happen for every single ammonia molecule. It happens for about 1% of them rather than all of them, and that's what makes this a weak base. But the hydroxide ion doesn't necessarily have to come from one of the species. It can be formed from water donating one of its protons to another species, and that is generally the case with the weak bases. So now that we've defined some of the characteristics of acids and bases and strong acids and weak bases, we're going to talk about the acid-base reaction you're going to be responsible for knowing how to write, and that is the neutralization reaction. And so neutralization reactions are what you get when you react generally one of your strong acids with one of the metal hydroxides. So for the most part, this is a strong acid and strong base interaction. It can happen with weak acids and bases, but some of those equations tend to get a little more complicated. So for us, we'll stick to, like I said, one of the metal hydroxides reacting with one of the strong acids that we saw on the list in a couple of the previous slides. As you can see, the general form, this happens in every acid and base neutralization reaction. When you mix the metal hydroxide with the strong acid, the hydroxide ion, the OH minus, and the hydrogen ion from the acid, the H from the acid part, they combine together and give us a water molecule. And the other two leftover ions, whatever ion is attached, whatever metal is attached to the hydroxides, and whatever anion is there with your hydrogen in the acid, they come together and form whatever salt or ionic type compound those two ions would join together and form. You would need to check and see if it is insoluble when you write these equations. If it forms an insoluble compound, you need to show it in the solid form. And of course, we write H2O as our liquid. In this case, we see the magnesium chloride that is formed is a soluble compound, so it stays dissolved in that water that is formed and is already part of the reaction. So we, again, in the neutralization reaction, you guys will have to write some of these. You'll always be using a strong base, one of the metal hydroxides, plus one of the strong acids that we find on any strong acid list. You can look at it previously in the presentation here. You can Google one yourself. They all have the same 6 or 7 compounds on them. And what's formed is a salt from the 2 leftover ions and a water molecule. We'll take a look at a couple of examples on the next few slides. Here we have our first neutralization reaction example. We are asked to find the balanced chemical equation for the reaction between sodium hydroxide and sulfuric acid. So they give us the formula for sulfuric acid, H2SO4. We will have to find the formula for sodium hydroxide ourselves. Sodium hydroxide, sodium is an Na+1 ion, and hydroxide is an OH-1 ion. So the formula for sodium hydroxide is therefore NaOH plus H2SO4, as we are reacting them together, yields. We know from the previous discussion that the products of an acid-base neutralization are water plus a salt formed from the combination of the leftover ions rather than hydrogen and hydroxide. So in this case, that would be sodium and sulfate. And of course, we want to balance our charges to make sure that we get the correct formula for the compound formed from ions of sodium and sulfate. That would be Na2SO4 because sodium is +1 charge and sulfate is -2 charge. Then we will finish the problem by balancing. I will count the elements as I come to them. On this side, I see 1 sodium. I see 5 oxygens. 1 here and 4 here. I see 1, 2, 3 hydrogens. And finally, I see 1 sulfur. On this side, I see 2 sodiums. Oxygens, I still see 5. Hydrogens, I only count 2, and still 1 sulfur. So if I try to go ahead and balance the sodiums, if I put a 2 there, I get 2 sodiums. I now have 2 plus 4, 6 oxygens. I now have 2 plus 2, 4 hydrogens, and I still only have the 1 sulfur. Now over on this side, if I try to do the same thing, maybe try to balance the hydrogens in the water. If I have 2 waters here, that will give me 4 hydrogens. That will also give me 2 plus 4 for 6 oxygens. I have 2 sodiums on either side. I have 6 oxygens on either side, 4 hydrogens on either side, and 1 sulfur on either side. So 2 NaOH plus H2SO4 yields 2 H2O plus Na2SO4 is the balanced chemical equation for the reaction between sodium hydroxide and sulfuric acid. The final common reaction type that we're going to cover is the oxidation-reduction reactions. These are often called redox reactions, and it was originally studied as reactions that involve something reacting with oxygen. And of course, oxygen is one of the biggest constituents of our atmosphere and much more reactive than the other big constituent, which is nitrogen. So Reactions with oxygen are both very common and some of the oldest studied reactions in all of chemistry. There are a lot now that are lumped in with that. They don't necessarily have to involve oxygen anymore. A lot of them still do, but they've grouped other similar reactions in with these also. And the main identifiers for these types of reactions involve electrons being transferred from one species to another in order to facilitate ion formation. And so the terms oxidation and reduction actually have meaningful definitions for this type of reaction. When we say something undergoes oxidation, that means it has lost its electrons or lost electrons to another atom or compound. And when something undergoes reduction, that means it has gained some electrons from somewhere. To determine if an oxidation-reduction reaction has taken place, we need to concern ourselves with what is known as the oxidation state of each species in a reaction. The oxidation state is the charge on a specific atom if it were in an ionic bond. Now, of course, not all bonds are ionic bonds, some are covalent, but oxidation state is somewhat like formal charge in that it's somewhat of a bookkeeping method. It doesn't mean necessarily that these atoms have these charges or states or anything, but it's a way to keep track of electrons in reactions. And so we can assign oxidation state using the following set of rules for any element or any atom in any compound. The oxidation number of an atom in an elemental substance is 0. So if an atom is just by itself or bonded to itself, like a metal atom by itself in a reaction, or for instance, an O2 or an I2 or a Br2 or something like that, in its elemental form, all atoms have oxidation states or numbers of 0. When we see a monoatomic ion in a reaction, something like an Na plus, or an SO42 minus, or an Na plus, or a Cl minus, or a S2 minus, the oxidation number of that species is its charge. So wherever it's a +1 or a -2, that is its oxidation number. Hydrogen has 2 cases. It's always a +1 when it's bonded to non-metals, and it's always a -1 when it's in a compound with a metal. Oxygen is almost always -2 unless it's bonded to a fluorine. Fluorine can alter that, but fluorine is really the only thing that can alter that. Halogens, so the things in group 17, fluorine, bromine, and iodine, are always -1. Unless they're bonded to oxygen. Oxygen can change that. And like we said, but oxygen cannot change fluorine. Fluorine is -1 always. And the final piece of the puzzle there says the sum of the oxidation numbers is equal to the overall charge on the molecule or ion. So if there's no charge indicated, like with most compounds, the overall charge is 0. So adding up all of the oxidation numbers in that species should add up to 0, and that's how you figure out some of the leftover ones. If we have an ion, a polyatomic ion in our chemical equation with a charge like a 2- or a 3- or a 1-, then all of the oxidation numbers in that compound should add up to that number, and that will help you figure out some of the ones that are left over there. For an oxidation reduction reaction to have occurred, then the oxidation state of something in that reaction must change from the products to the reactant. So we must have a change in those oxidation numbers somewhere in order to claim that an oxidation reaction has taken place. Now, we'll practice on the next couple of slides counting some oxidation numbers in certain species, and then we will look at some of the reactions. You'll be asked to identify some oxidations and reductions in your work, but you will not be asked to write out an oxidation reduction equation, and we'll see some samples of identifying the oxidants and reductants a little bit further down the presentation. All right, so here on this slide, we're going to determine the oxidation numbers of all of the species that we see here, or all of the atoms in the species that we see here. So the first one we're asked to identify is the oxidation numbers on the atoms in the H2S molecule. So we can see, or we'll keep in mind, that H2S, there is no charge given there, and so this is a neutral molecule. All of the oxidation numbers in this compound should add up to 0. We remember from the previous set of rules that when hydrogen is bonded to nonmetals, as it is here, it's bonded to a sulfur atom, then its oxidation number is +1. So each of the hydrogens there have oxidation numbers of +1. Since there are two of them, to figure out what the sulfur is, we take into account that all of the oxidation numbers must add up to the charge on this molecule. And since the charge on this molecule is neutral or 0, then it should be H plus S equals 0. We already know that each of the hydrogens are +1, so +1 plus +1 plus whatever the oxidation number on S is should equal to 0. +1 plus +1 is of course +2, so 2 plus S is equal to 0. Therefore, the oxidation number on the sulfur atom is -2. So in the H2S molecule, each hydrogen atom has an oxidation state of +1, and the sulfur atom has an oxidation state of -2. Now we will look at the sulfite ion that we see there, SO3, with a 2- charge. We know from the previous set of guidelines that oxygen is almost always -2. The only time that changes is when it's bonded to fluorine, and it's not bonded to fluorine here. So our oxygens must all be -2. We also know from the previous set of guidelines that the total sum of the oxidation numbers has to equal the charge on the molecular ion. In this case, the charge is 2-. So since we have 3 oxygen atoms, each with a -2 charge, plus the sulfur atom, we should reach a total of -2. -6 is the total of the oxygen oxidation states plus whatever oxidation state sulfur happens to be, should equal -2, which means sulfur has to have an oxidation state of +4 in the sulfite anion. In the final example we have here, we can see that we have sodium sulfate in a 2SO4. We know from the set of guidelines that if we were to treat this as an ionic species, we can say that each of the sodium atoms have a +1 charge. And the oxygen atoms should have a -2 charge. There are 4 of them there. So we know that This is a neutral compound as there is no charge indicated, so we should see 2 plus -8 plus whatever the oxidation state of the sulfur atom is should equal to 0. 2 plus -8 is -6. So -6 plus whatever the oxidation state of sulfur is should equal 0. Sulfur therefore has to have an oxidation state of 6 in this compound. Here on this slide we have a few definitions before we go to identifying the oxidizers and reducers in oxidation or reduction reactions. We want to make sure that we have our definitions straight. Because these are complementary processes, you always have an oxidizer and reducer in the oxidation reduction reactions. To review, when something is oxidized, it loses electrons and it increases in oxidation number. That just happens. When something is reduced, it decreases in oxidation number and gains electrons. However, it kind of feels backwards to describe each of these things. The thing that is reduced is ended up being referred to as one of three things, either the oxidant, the oxidizer, or the oxidizing agent, because the thing that is the reduced, the thing that gains electrons, it gains those electrons from the things that lost the electrons. So we say the reducer oxidizes something. So it works for the vice versa also. The thing that is oxidized, whatever species is oxidized, is referred to as the reductant or the reducer or the reducing agent, because it is what is actually taking those electrons. It's oxidizing something else or causing something else to become oxidized. So be careful with those terms. It's easy to get those turned around. Whatever is reduced is the oxidizer. Whatever is oxidized is the reducer or reductant. So we have our first example. We have the simple reaction of solid sodium metal with chlorine gas to form some sodium chloride. We're going to try to determine if this is an oxidation or reduction reaction. First of all, we're going to check our oxidation numbers and see if they change. And then after we do that, if it is a redox reaction, we want to be able to identify the oxidizers and the reducers. So we'll start with our oxidation number, and we kind of go back to remembering our guidelines from earlier. We will see that for both of our elemental substances, so here in these instances, both of these are substances in their elemental form. So in both cases, on the reactant side, sodium has an oxidation number of 0, and chlorine has an oxidation number of 0. And that's because they are in the elemental state in the reactant side. Now, on the product side, let's try to figure out if they were oxidized or reduced. Did their oxidation number change? So on this side, we see an ionic compound formed of two ions, two monoatomic ions. Specifically, in this case, there are no polyatomic ions there. And we remember from the guidelines, the oxidation number of a monoatomic ion is equal to its charge. And so in this case, the sodium ions have an oxidation number of +1. And the chlorine atoms have an oxidation number of -1. So we can see there is a change in oxidation state for each of the elements present across this reaction. So it can be referred to as an oxidation reduction reaction. Now, we are going to try to identify which elements were oxidized and which were reduced. In this case, the oxidation state of sodium increases from 0 to +1, indicating that sodium was oxidized. I'm going to write that here. Sodium was oxidized, and chlorine was reduced. All right. So, and going back to our terminology there, if sodium was oxidized, it had to be oxidized by something, and that something was chlorine because chlorine changed. So chlorine is the oxidizer, and sodium is the reducer. And there we have it. We've identified this correctly as a redox reaction, an oxidation reduction reaction, in which one or more atoms had their oxidation state changed from the reactants to the products. Sodium had an increase in oxidation number, indicating it was oxidized by losing electrons. Chlorine had a decrease in oxidation number, indicating it was reduced by gaining electrons. Chlorine is the oxidizer or oxidizing agent, and sodium is the reducer or reducing agent. Here on this slide, we have a little bit more complicated example. We are asked to find the oxidizing agent given the following chemical equation. For problems such as this, we will want to go through and count the oxidation state for every atom in every compound. So of course, we'll start with the MnO4 species here. MnO4 is a polyatomic ion with a charge of -1. So everything in that species, all of the atoms must have their oxidation numbers add up to -1. Well, there are 4 oxygen atoms, and we learned that oxygen has an oxidation state of -2 in almost all situations, for a total of -8. So if the 4 oxygen atoms have -8 oxidation, and the entire oxidation number has to add up to -1, that means the manganese atom, let's make sure we know that's oxygen, the manganese atom has to be +7 to arrive at the total of -1. Now we'll look at chlorine. Chlorine has a -1 charge. That is a monoatomic ion there with a charge on it. And per the guidelines, the oxidation state of a monoatomic ion is its charge. Now let's take a look at the oxidation states of the species in the water molecule. In water, oxygen, as almost always, has a charge of -2. And our hydrogens would need to be +1. The guidelines say when they're attached to a nonmetal, they're usually +1. In this case, it is still the same. We also will know that because there's 2 hydrogens there. The oxidation of oxygen is -2, and the overall total has to be 0 since water is a neutral molecule. Now we'll look on the other side and see kind of what has changed. In our new MnO2 species, we have a neutral compound there, so the oxidation states must add up to 0. There are 2 oxygens at -2 apiece because oxygen is always -2, for a total of -4. If the total oxidation state must add up to 0, that means that manganese now has an oxidation state of +4. In our next species, the chlorine, or the chlorate ClO3 1- ion, I messed that up, let's rewrite that. All right, so the ClO3 1- ion, the chlorine, well, let's do oxygen first. Oxygen, there are now 3 of them with -2 charge or -2 oxidation apiece for a total of -6 oxidation. If the total oxidation on the whole ion is 1 minus, that means that the total oxidation of each atom has to add up to 1 minus, which means chlorine is in a state of +5. And then finally, we have an OH, we have the hydroxide ion, OH 1 minus. And if oxygen is -2 as always, then our lone hydrogen has to be +1 still. Now that we have the oxidation numbers laid out, we can see what has changed. The manganese from the MnO4 species has a reduction in its oxidation number. So therefore, that species is reduced. Mn is reduced. If something is reduced, something else must be oxidized. The only other change that we see in oxidation number for each atom here is the chlorine. Chlorine goes from -1 to 5. So Mn is, or sorry, not Mn, chlorine chlorine is oxidized. All right, we can see that manganese is reduced in this reaction and chlorine is oxidized in this reaction. Now here comes the part where it's a little bit tricky on the terminology. We often call the species that the reduced atom is part of as the oxidizing agent. For instance, here in this case, this is the species that manganese is originally a part of. And since manganese is doing the reducer, it is what is oxidizing, but we consider this whole compound the oxidizing agent. And so the answer to this question is A, MnO4, because it originally contained the atom that is reduced. The compound or species that originally contains the atom that is reduced is the oxidizing agent. Furthermore, if we were asked what is the reducing agent, we can say the chloride ion here is the reducing agent because it is the species that originally contains the atom that is oxidized. So it reduces the manganese in MnO4. Conversely, the manganese oxidizes the chlorine in the chloride ion, making MnO4 -1 the oxidizing agent. One final note I want to make before closing out this presentation is that the original reactions that we began this whole discussion with, the combustion reactions, we specifically looked at the combustion of methane, but combustion reactions in general, like I said, we talked about oxidation reactions got their names because of so-called reactions with oxygen. Perhaps the oldest known identified chemical reaction is the combustion reaction, the what we call the production of fire, what we may know as the production of fire. And that has a general reaction form, hydrocarbons, something made of carbon and hydrogen, oftentimes long chains. That's what living cells and things are made out of. So, of course, that's what fuels, think wood and even coal and stuff is made out of long chains of carbons. And so when that stuff reacts with the atmospheric oxygen, usually it needs a spark in order to initiate the chain reaction. The fuel is oxidized by the oxygens, resulting in the production of carbon dioxide and water, along with the heat and light we are so familiar with. So this is just perhaps one of the oldest known chemical, or one of the oldest thought of chemical reactions, and it just so happens that it's an oxidation reaction, and that reaction with oxygen is where everything gets its name.